All right, okay, so today we're starting a new chapter, which is limit theorems. The first thing we have to do in order to start talking about limit theorems and prove limit theorems is talk about two major probabilistic inequalities, okay? The first of them is Markov inequality. This is typically a loose bound on the value of a non-negative random variable x with a known mean expectation of x. Okay? So here's the inequality. If the random variable x is non-negative, that is, it can take only non-negative values, then the probability that x exceeds a certain positive value a is upper bounded by expectation of x divided by a. This is true for any random variable x that's non-negative, irrespective of the particular distribution of x. Let's quickly prove this. Here's what we can do. Define fa of x as being equal to a if x is bigger than or equal to a, and 0 if x is less than a. So what did I do? I defined a function of the random variable x that just sets it to two values. If x happens to exceed the level a, f of x is set to a. Maybe let's call this g. Let's not. Yeah, I mean, this is a proof device, okay? I just want to prove this inequality, and this is the way I do it, okay? You can do it in different ways as well. No, that would cause a problem. So a is a constant, okay? So a is a real constant, and it's non-negative. We just defined a random variable that takes two values. Okay, so g of x, as you pointed out, it's a random variable. Okay, and it takes two values. In particular, I know that g is always less than or equal to x, right? Because if x exceeds a, g is set to a. If x is lower than a, g is set to 0. So g is always less than or equal to x. Do you agree? Does everybody agree? Okay. So I can also then say that the expectation of g is less than or equal to the expectation of x. Right? Now let's compute the expectation of g. That's easy. G takes two values. It's a with a certain probability and 0 with another probability. So this is a times the probability that x is bigger than or equal to a. Right? Because g takes the value a whenever x is bigger than or equal to a. So the expectation is a times the probability of this event plus 0 times the probability of this event, which is 0. Okay, so then I get that this is upper bounded by expectation of x, which implies the result that we're trying to prove. The probability that x is bigger than or equal to a is upper bounded by expected value of x divided by a. This is true for any random variable x. What does it use? It just uses the expectation. So it's typically a loose bound. Sometimes it's useful, but it's usually a loose bound. Let's just see an simple example of it, of its usage. So x is uniformly distributed in 5 to 10. So here is my PDF. This is 5, this is 10. And this is fx of x. It's equal to 0.2 in this range. Okay. Now let's compute, for example, using this. Well, first of all, what is the expectation of x in this example? Great, 7.5. Okay. So now let's try our Markov inequality for different values of a. Suppose a is, I don't know, set a to 5. We can do this, right? A is 5. What is the probability that x is, so the probability that x is bigger than or equal to a must be upper bounded by the expectation of x divided by a. So in this case, the probability that x is bigger than or equal to 5 is less than or equal to 7.5 divided by 5. What is this? 1.5. So what does this tell us? It tells us nothing. It just tells us, in this case, that the probability is less than or equal to 1.5. In this case, the bound isn't telling us anything that we don't already know. So this is uninformative for this value of a. It doesn't give us any information for this value of a. We already know, by the way, this is equal to 1. Okay. Now, how about, let's try a equals 7.5, exactly the mean. What does that give us? The probability that x is bigger than or equal to 7.5 is less than or equal to 7.5 or 7.5, which is 1. Again, it's not telling us anything because we already know that probabilities are upper bounded by 1. Again, this is uninformative in this case. Let's try something else. Let's try, for example, a equals 9. Now, the probability that x is bigger than or equal to 9 is upper bounded by 7.5 divided by 9 is what our bound says. What is this? This is 0.83, roughly. Okay. So the probability that x exceeds 9 is not more than 0.83 is what it says. It's correct. However, it's really still quite far, still quite loose because we know that this probability is actually equal to 0.2. Right. So, this just shows us the limitations of Markov inequality. The Markov inequality can be more useful for other distributions, but most of the time it's going to be loose. So why did we do this? The main reason we're covering Markov inequality is because we'll use it as a step to reach the Chebyshev inequality, which is a very important classical inequality that you should take away from this course. Okay? So the Markov inequality, let me repeat, is only valid for positive random variables. In other words, non-negative random variables. But the Chebyshev inequality is valid for any random variable. Let's just easily derive this. Here's how we derive the Chebyshev inequality. So apply Markov inequality to x minus expectation of x squared. Okay? So x minus expectation of x minus expectation of x squared is a random variable. Why? Because it's a function of the random variable x. We don't know what x is. X is any random variable, not necessarily positive. Okay? So we define y, which is the expected value of x minus expected x squared. What kind of random variable is y? Y is non-negative, right? Y is always non-negative because we defined it by taking the square. Okay, great. So we can apply Markov's inequality to y. How do we do that? We need the expectation of y, of course. What is the expectation of y? It's the expectation of x minus expected x squared, right? So the expectation of y is expected x minus expected x squared, which, if you don't know this, you're in trouble before the midterm. Right? What is this? This is the variance of x. Okay, so let's apply Markov's inequality. The probability that y is bigger than or equal to a is less than or equal to the expected y value of y over a for any positive number a, positive scalar a. Now, the probability that y is bigger than or equal to a, we can rewrite this. Oh, wait. Let's apply, so rather than a, let's use a squared here. Why not? Okay, okay, let's use b. Okay. And let b be equal to the square of some scalar. Okay, no problem. We're just using Markov's inequality with the scalar b, and b happens to be the square of a scalar a. B is positive. Okay? Right. So now, the probability that y is bigger than or equal to b, we can write as the probability that x minus expected value of x squared is bigger than or equal to a squared, right? This is less than or equal to the variance of x divided by a. Okay? Squared. Right. Now, so I can write these events, equivalently as the probability that the absolute value of x minus e of x being greater than or equal to a. Remember, I defined a as a positive number. This is less than or equal to the variance of x divided by a squared. Okay? If you want, we have defined the variance as sigma squared, write this as sigma squared divided by a squared. This is called Chebyshev's inequality. It's a very useful inequality that uses, in addition to the mean of the random variable x, also the variance. So I expect this to be stronger than the Markov inequality. Markov inequality uses only the expectation, which is a first order statistic for the random variable, and it doesn't, as we've seen before, doesn't distinguish different distributions. It may not distinguish different distributions very well. On the other hand, the variance is a second order characteristic. Together with the mean, it's going to better distinguish a distribution. Okay? So this carries more information about the random variable. It's usually a better bound. Okay? It's always a better bound than the Markov inequality, but always as good. And this is usually useful, as we will now see in an example. Now, so let's understand this. Give me any random variable. The probability that the random variable deviates from its mean in absolute value by more than a certain amount is upper bounded by the variance of the random variable scaled by 1 over that amount squared. Okay? So the upper bound becomes worse, of course, when this grows. When does this grow? This grows with variance. So the more the variance of the random variable, the more its tendency to be outside of a certain window around its mean. Okay, the more the variance, the more it's expected to be. So this is the relationship. So if so far variance did not mean a lot to you, I think this is a very good way of understanding what variance is doing. Okay, the probability that x is expected to be, the probability that x is outside a certain window of size A around its mean, is upper bounded by its variance. Of course, the more you increase this window, the smaller the probability will get. So this is consistent with a squared in the denominator. So let's just apply this to the Gaussian distribution. And I think it's going to be more concrete when we do that. So the exercise is to use Chebyshev's inequality to lower bound the probability that a Gaussian is within 2 standard deviations of its mean. Okay. This is something I think you all intuitively had an idea about so far, but we never placed a value on this. We never addressed this numerically. So this is when we address this numerically. Okay. So let x be any Gaussian. Okay. It's normal with some mean mu and some variance sigma squared. What do I need? I need the probability that x is, this is mu, x is outside of a certain window around the mean. Let me center this properly. This is mu. Okay, and suppose this point is mu plus 2 sigma. What is the standard deviation? Standard deviation is sigma if the variance is sigma squared. Okay, and this is mu minus 2 sigma. I basically want. Okay, let me read the problem statement once again. The probability that it is within 2 standard deviations of its mean. So 2 standard deviations is 2 sigma. Okay, within 2 standard deviations away from its mean means x minus mu in absolute value is less than or equal to 2 standard deviations. This means, so if this happens, x is within its mean by 2 standard deviations. X is within 2 standard deviations of its mean. Okay, so we want to bound this probability. What can we do? Well, this is 1 minus the probability that x minus mu is bigger than 2 sigma, right? Now, the probability that x minus mu in absolute value is bigger than or equal to 2 sigma is, by the Chebyshev inequality that we just proved, is less than or equal to, what is the variance of x? It's sigma squared. What is the square of this value here? It's 2 sigma squared, so 1 over 4. what did we just show? We showed that the probability that x is outside of 2 standard deviations away from its mean, it's more than 2 standard deviations away from its mean, cannot be more than 25%. Okay? So by the continuity of x, this is also true if we replace this by a bigger than. Okay? So it just tells us that this is less than or equal to 1/4, which means that 1 minus this is bigger than or equal to 3/4. Okay? So basically we just showed using Chebyshev's inequality that the probability that x is more than 2 standard deviations from its mean is upper bounded by 25%. So it's going to be in this region by probability less than 25%. So it's going to be here in this green region with probability at least 75%. Right? That's good to know. How about, for example, the probability that the Gaussian is within 3 standard deviations of its mean? Right, 8/9. So it's 8/9. There's 8/9 probability that the random variable, Gaussian random variable x will be within 3 standard deviations of its mean. So if you consider the remaining 1/9 negligible in practice, you could make computations based on the assumption that x is within 3 standard deviations of its mean. So this tells us that the tails of the Gaussian, so these tails, are not very thick. Okay, the tails decay pretty fast in the Gaussian. It's not a heavy tail distribution, as we say in probability language. Okay. So that concludes our discussion of these 2 inequalities, which we will need for our probabilistic convergence discussion. So probabilistic convergence, as I said, is an important step connecting the probability theory that we've covered so far with the real-life convergence phenomenon that we see, but we so far don't know how to address mathematically. Okay, so let's first remember the definition of the convergence of a deterministic sequence of numbers. You know this from basic calculus, right? So let a sub n, indexed by n, be a sequence of numbers such that, right, so they are indexed by n. Limit as n goes to infinity a n is equal to a means that for every epsilon there exists a number n sub 0 or n naught such that for n bigger than n naught, a n is within epsilon of a. Okay, so let's remember this basic convergence. So here is the level a. A is a scalar, and my sequence a sub n is taking different values as n grows. So I say that my sequence, and sometimes you can take big values like this, I say that my sequence converges to A if no matter how small a window around A I pick, eventually my sequence will enter this window and will not go outside that window again. That's the usual notion of convergence from calculus, right? Let me repeat. So if for every positive epsilon there is a index and not of epsilon, such that for all and after that index, I have a n minus a being within epsilon. Then we say that an, the sequence an converges to the number a as n goes to infinity. Okay. Now that's for deterministic sequences. What do we do for random numbers? A sequence of random variables. So the last notion that we will define today is the notion of convergence in probability. Okay. So I would like you to think about a sequence of random variables. Instead of a sequence of numbers, consider a sequence of random variables. Okay. y1, y2, y3, y4. Okay. To motivate you, I can give you an example. So you're taking averages. Every day for example, you take the, you get one more sample of something and you take the sample average so far. What can that be? For example, every day you run a certain distance, okay, and you average your time for running that distance. There is some randomness in your, time that you achieve every day, okay. But if you're not getting any better as an athlete, if you take averages long enough for a sufficient number of days, you sort of expect the average to converge. Okay, so y sub y1 could be your first, average of just one sample. y2 is the average of 2 samples. y3 is the average of 3 samples. y4 is the average of 4 samples, etc. So they're all random variables, but I can list them as a sequence. Okay. Now, this sequence converges in probability to a number a if for every epsilon the probability that my random variable exceeds a by more than epsilon goes to 0. Okay. The notation is yn goes to a in probability. So now probability that yn minus a is bigger than epsilon. This is a number, right? This is a number b sub n, because it's a probability. It's a number between 0 and 1. So I have a sequence of bn's. If bn as a sequence, as n goes to infinity, converges to 0 for every epsilon, no matter what epsilon is, then I say that yn converges in probability to a. Let's just see an example. I think the best way is to make this concrete with an example. So here's the example. Suppose for each n, yn takes the value n with probability 1 over n, and the value 0 with probability 1 minus 1 over n. Does yn converge, and if so, to what? So let's see this. Let's look at the probability mass function of yn. Yn is equal to n with probability 1 over n, and it's 0 with probability 1 minus 1 over n. Okay? Then, so it has a PMF, Pyn of k, as a function of k, that looks like this. It's equal to n with probability 1 over n, and it's 0 with probability 1 minus 1 over n. So for y1, it's either 1 or 0. For y2, it's either 2 or 0. For as n grows, this value grows, but its probability reduces. So the probability in this case gets collected right at 0. My guess is that yn converges to a value. What do you think that value could be? As you increase n, it's more and more likely that yn, the random variable you have, will take the value 0. So I believe that yn will converge in probability to 0. So let's check this. Let's compute the probability that y sub n minus 0 is bigger than epsilon. Epsilon is any positive and arbitrary positive number. The probability that yn is bigger than epsilon in absolute value is basically the probability that yn is not 0, which is 1 over n exactly. So this means that the limit as n goes to infinity, the probability that yn minus 0 is bigger than epsilon goes to 0, because this goes to 0. 1 over n goes to 0 as a sequence. So this means that yn converges to 0 in probability. So next time we'll address this as well as other notions of convergence, and we will see a very important special case of the convergence in probability, which is the weak law of large numbers. Okay? So I'll see you next time.